Cool. Hello, everyone. My name is Gianmarco Visani. I'm currently a junior at Tufts studying computer science and physics. And today I'm going to talk about my Laidlaw research, which is using positive, unlabeled, and hard negative examples for hierarchical classification of enzyme promiscuity. And I performed this research with the help of my mentor, Professor Soha Soon from the CS department, and with the collaboration of another CS professors, Michael Hughes. And I promise to you, by the end of this presentation, you will understand what the title means. I know you might be scared. Okay, so let's start with some background information. So the main tool that we use is classification, which is a machine learning technique aimed at assigning data to the correct classes. So the easiest example possible is we can train a machine learning predictor to distinguish between images of cats and of dogs. And we do so by training this predictor, giving it a lot of images of cats and dogs and telling them these are cats and these are dogs. And this predictor learns what it means to be a cat, what it means to be a dog, so that when we make a prediction, we give it an image that it has never seen before, and it's able to classify it correctly, in this case, as a cat. That's right. So classification has been used in a variety of applications. It's in your smartphone, it's in everything. And in my research, I used it to predict the enzyme activity on any given molecule. So now a little bit of background on the biology of this. So enzymes are protein responsible for catalyzing biochemical reactions in all living organisms. They work by binding with a molecule, also known as a substrate, and transforming it into another molecule, also called a product. And when the enzyme does this, we say that the enzyme acts on the substrate. For long, the enzyme function has been considered to be specific, which means that we thought that enzymes were able only to act on the particular substrates that they evolved to act on. So they evolved to act on one substrate to catalyze one reaction in nature, and so we thought they were not able to catalyze any other reaction. In biology textbooks, this idea is commonly referred to as the lock and key model of enzyme function. However, reality is actually more complicated than that. Enzymes have been found to engage in promiscuous activity. In particular, we refer to substrate promiscuity as the ability of enzymes to act on substrates other than the ones they evolved to act on. So they can act on substrates that they don't see actually in nature. For example, lactate dehydrogenase is responsible for acting on lactic acid in nature, but it's been found in lab experiments to be able to act on a lot of other molecules. And most enzymes, or a big proportion of enzymes, have been found to actually have this ability to act with other substrates. So why is substrate promiscuity important? So the fact that enzymes can act on many more molecules than we thought possible means that we can use enzymes much more efficiently and much more broadly for biological engineering. For example, if we want to degrade a molecule, if we want to produce a molecule that is not easily found in nature, we can just find the right enzyme and making it act on the right molecule in order to create what we want. This will be very useful, for example, for making compounds for pharmaceuticals or in a variety of other industries. So the only problem with this is that it's expensive to perform lab experiments to find the right enzyme for whatever job you want it to do. So a cheaper approach would be to try to develop an understanding, a characterization of enzyme promiscuity using computational approaches. So the goal is to know if, and possibly even why, an enzyme will act on any given molecule. There's a lot of work that's been done in this field. I just put here some meaningful examples. The first example, fun fact, is something that my mentor worked on a few years back. And there's all previous work. The previous work is very varied and it has a lot of shortcomings. The main one of which is the fact that most of it is focused on smaller subsets of enzymes. So for example, the tool that my mentor developed, Proximal, only is specific to a subclass of enzymes that is known to be broad, or other machine learning techniques have been used, only a limited sets of enzymes due to data availability. So there's no comprehensive characterization on enzyme function. There is no tool, general tool to predict the activity of any enzyme. This is what we've been trying to solve. And our approach is pretty simple. We give me an enzyme and a molecule, and I want you to, I will tell you whether the enzyme will act on the molecule. In machine learning land, this is simply a binary classification problem, which I mentioned to you earlier. So for every molecule and for each enzyme, we want to predict whether the enzyme will act on it. So we say that if the enzyme acts on the molecule, that's a positive molecule. If the enzyme does not act on the molecule, it is a negative molecule. So with this approach, we effectively built one predictor per each enzyme. I want to emphasize that this is a data-driven approach, so we do not actually model what the enzyme is. We just have a lot of examples of which molecules the enzyme acts on, and with machine learning, we're able to predict which other molecules the enzyme will be able to act on. The data that we used come from Brenda, which is a database cataloging known natural and promiscuous reactions that most enzymes act on. The first summer was spent actually pre-processing, collecting, analyzing, and pre-processing all this data in order to get useful representations that we could use for machine learning. And the main focus of that was to minimize the loss of data during this pre-processing, because Brenda only gives me known common names of molecules, and from that we needed to reach a universal representation that we could use in machine learning. After the pre-processing, we found that we had enough data for about 1,007 enzymes. I want to emphasize that this is unheard of before. All previous work only focuses on smaller subsets of enzymes, so this is the first time we were working with a very big chunk of enzymes. Of course, this is the real world, so there were problems with the data we collected. First of all, many enzymes do not have a lot of data. Maybe because it was not cataloged, maybe because we lost it during the pre-processing. So a lot of those 1,007 enzymes didn't have a lot of data to work with for machine learning purposes. And the second big problem is that there is no comprehensive database for negative molecule. Like there's no database that tells me, oh, this molecule does not interact with this enzyme, because it's usually not very interesting, but we needed it from our machine learning purposes. And so what we actually had to work with was unlabeled molecule, which are molecules whose label is not known. We just know that they haven't been found to be positive, but they might as well be positive. Maybe they just were not found to be so yet. We treated unlabeled molecules as negative with some variations, which I'll explain in the future. Also because one would expect to find more negative molecules than positive ones. One would expect to find more molecules that enzymes do not act on than molecules that enzymes act on. So we developed three contributions in order to tackle these problems, and I will briefly explain all of them. So the first of them is we integrated the use of inhibitors in our training. So inhibitors are a special class of molecules that bind with enzymes, like the positives do, but no transformation happens. So they're actually negative, but they must have some characteristics that makes them closer to the positives. In machine learning land, this kind of example is called a hard negative example. And its main property is that it lies very close to the decision boundary between positives and negatives. So using it during training can help better characterize, better define this decision boundary for the classification purpose. So, and the second contribution was exploiting the hierarchical classification of enzymes. So enzymes are universally classified by the Enzyme Commission classification, which assigns to each enzyme a unique identifier. It's called an EC number, and it's composed of 4 individual numbers separated by a period. And each number represents a higher degree of specificity of enzyme function. So there's 7 main classes, and each of them represents a broad family of reactions, let's say, and then every time we go we add a number, we get more specific until we get to the full enzyme with the 4 numbers. So effectively, this creates a hierarchy of enzyme function. And our model that we built mimics that hierarchy. We actually trained a predictor at each level of the hierarchy, and we allowed all predictors to exchange information across the hierarchy in order to make a better use of the data. So for example, if we did not have a lot of information for one enzyme, if we were able to make a decent prediction one level up, that means that we had prior information about all its children. And this is much better than just starting from random and building only one predictor at this level. Then the third contribution is pretty straightforward. So instead of considering unlabeled molecules to be simply negative, we consider them to be negative up to a certain percentage of confidence. So we define this confidence via similarity information. So each unlabeled, the general idea is that the more similar an unlabeled molecule it is to the positive molecules, the less confident we are about it being negative. So that goes the other way around. If it's not very similar to the positives, then we're more confident than it is negative. So we evaluated our model by testing it, by making predictions on some data that we saved aside for testing. So it's data for which we know the true label, if it's truly positive or truly negative. And we also made predictions with a baseline model, which is just a model that is analogous to ours, but does not have our 3 key contributions. And we evaluated each contribution individually as well as all together. We found that all our contributions improve performance. Some are better than others. The hierarchical structure is the one that delivers the best performance. But the best model has all 3 contributions in it, and it allows us to predict the correct answer to correctly predict enzyme activity on a molecule about 92% of the times, which is very good considering that we do it on over 1,000 enzymes out of 6,000-7,000 that there are. So to conclude, now we have a tool that could actually allow us to predict the enzyme activity on any given molecule, and we can do that for about 1,000 enzymes. And this tool will soon be available on a website. In our lab with my mentor, we're working on building a web tool to put this tool and other tools on. Also, some enzymes were easier to characterize than others. This 92% is average across all 1,007 enzymes. So some of them actually are at 100%. Some of them are at like 85%. So a good object of future work would be to understand why some enzymes are easier than others. And then I want to just finally emphasize that this is a fully data-driven approach. We did not make any assumptions on what enzymes we were using. If we had the data for it, we built it. And this easily scales when we have more data available. So say that in the future, we get a bigger database with more example reactions, more substrates. We could retrain our model on that new data and maybe actually make predictions for more than 1,000 enzymes and maybe even with better accuracy. So I want to thank you, the Laidlaw Foundation, Don, Diana, my mentor, and all of you for listening to me today. Thank you.
Thank you. Oh, yeah, questions?
I have some chemistry questions, especially about like how you would input certain information. I think of like molecules, and I'm thinking about like the way in which one molecule might have many rotamers and might just be moving around in space. And because of its spatial conformation, that's the only reason why an enzyme could act. So how do you account for, despite the fact that that molecule is, let's say, an inhibitor, but it's only an inhibitor when it's in some certain conformation? So how do you distinguish between that?
Okay, so the way we represented molecules is by using fingerprints. You know what fingerprints are?
Like a fingerprint? Like
No,
this,
not that. Okay.
I'm not
no, okay. So a fingerprint is a binary vector of features, and there's different kinds of them. Most of them only represent information in 2D. So for example, feature 1 is, does this molecule have an OH in it? Does this molecule have this particular substructure in it? There's different kinds of fingerprints. Some of them are 3-dimensional. Most of them are 2-dimensional. So the idea is that we use the kind of fingerprint that has for each feature one particular substructure, but it is two-dimensional, so it would not account for the conformation you're talking about. So maybe using different kinds of fingerprints can input that information into it. So we do not specifically account for it. We let the fingerprint tell us what to do. Yeah, and also like this work is in the field of systems biology, or more broadly bioinformatics. So we're more CS people. So now we're actually trying to work and see, to talk to some biology people and say, okay, so how can we validate our work? What else can we do to validate this? What else can we do to improve this?
And then if I can, I have a follow-up question too. When you're talking about inhibitors, like, are you classifying by different types of inhibitors? Like if something is allosteric but is not binding in a pocket where activity is happening where the enzyme reaction would happen, or like, is that a factor?
No, we just consider all inhibitors to, we didn't classify between different inhibitors. We just consider all of them to be negative as they are.
Okay, thank you.
Sure.
So my question is not about biology. So specifically with the machine learning techniques you're using,
yeah.
I have a couple questions, but it seems as though you're using like a tree-based approach.
Yeah.
So what specific methodology were you implementing?
So I'm assuming you know about machine learning if you're asking this question?
I know a bit, yeah.
Okay. So this is a kind of hierarchical classification. So what we do is we use random forest classifiers, which are a type of machine learning model. What we do actually is we make a prediction, a probabilistic prediction, because random forest classifiers does not output just 0, 1, it outputs a probability. Right. We make a prediction at the top level of the hierarchy, and then we calculate a residual after that prediction. So for example, if a molecule, its true label is 1 and it's predicted to be 0.6, at that level, its residual is going to be 1 minus 0.6, which is 0.4, right? And then at this level, we don't train a classifier, we actually train a regressor, which does not, which learns real numbers for each feature, for each molecule. And so we make it learn that 0.4 residual, right? And so when we want to make a prediction at this level, we add the output at that level and the output of this at this level, right? And then we keep doing it until the end. Yeah. Does that make sense?
It does, and I think that the methodology you're using makes sense given the hierarchical nature of the enzymes that you're trying to classify. A question I think you answered in your talk was whether or not you consider the fact that there might be some error in your initial classifiers that you're trying to predict. So like your 1s and 0s for in like your Y vector essentially might actually be mistakenly characterized.
Yeah, the negatives are actually unlabeled. That's what I said. Like we treat them as, so naively you can just treat them as negative, although some of them will be positive. Right. There's actually a whole field of machine learning called positive unlabeled learning that has a lot of different techniques to do this. And how we quote unquote solve this is we apply a confidence weight to each unlabeled example. Yep. So the unlabeled example is, its label is negative, it's 0, but it's got a confidence weight to it. So during training, it's actually considered less or more based on the confidence. So for example, then all inhibitors and all positive examples had a confidence of 1 because we're confident in that label. So during training, they are of more importance, quote unquote. Instead, the unlabeled are of less importance according to this particular confidence score.
Yeah, and that makes a lot of sense. And then the last question I had was, are you more concerned with type 1 or type 2 errors? So are you more concerned with positive, false positives or false negatives in this application?
So that's a good question. We talked about this a good amount. So when in the results here, I only show this number, 92% accuracy, but the actual results are much broader than that. So one thing that we did, that you do in machine learning, is you calculated a precision recall curve, which just And we actually maximize for precision and for the area under the precision recall curve, which is maximize the trade-off between false positive and false negative. So we specifically aim for that. Like, I think to answer that question better, one needs to, from a like usability standpoint, what do I care about most? Do I care about being precise, or do I care about identifying each individual one? Or do I, like, if out of 1,000 I tell you that 20 are correct but only 10 actually are, so it's not very precise, but I can narrow down my search space. So that is like, not being a biologist nor a chemist, I don't really know how to answer that question. So we just optimize for that trade-off instead of for one specific one. Yeah, exactly. It does. It's not clear-cut in this case, as it is, for example, if you do classification to detect cancer, of course, you want to detect all of them. But we did ask that question a lot of times. We weren't sure what one would do. Yeah. Thank you.
Okay, I'm going to preface this with not understanding CS or chemistry, so
Cool.
Forgive me if it doesn't make sense. But does this give you any information about why it rejects certain enzyme molecule combinations that then could be used?
I'm glad you asked that question. So what we might do in the future is actually answer that why. And so, as I said, each molecule is represented by a binary vector, and each feature of the vector is a feature of that molecule. So an idea would be, okay, let's try to understand which features matter most, right? Does that make sense? Is that what you're asking? Right. So there's a lot of ways of doing it. We will probably look into it. It's not very easy to do, and we will need to ask some biologists, some chemists, like, once we get some results, and ask them, does this actually make sense? Like, is this relevant, right? It's not as straightforward to do it with the method that we did. You know, each machine learning model has different math behind it. For some of them, it's very easy. You can just look at it and just calculate which one are most important. In our case, we will have to do some heuristics. We will have to test it and figure something out. This is actually like a very, very big theme in machine learning now. It's like understandable machine learning, which is like, usually you see this as a black box, like it works, period, right? But you kind of want to understand why it works. It's a big area of research. I kind of want to look into it. My mentor is looking at me and smiling. I don't know if she wants me to do it, but does that answer your question? Yeah. Thank you.
Any other questions? Okay, I've got two. One of them that is probably pretty quick. You said that the balance between false negatives and false positives was trying to be, you tried to optimize it for it. But is it possible, and it sounds like it is, to rerun it and actually weight it towards one or the other?
Absolutely. Yeah.
Absolutely. If you're doing cancer research, you weight it towards one, but if you're doing another type of research, okay.
Absolutely. So, it takes a little bit of time, but yeah, you can do it.
But it's still cheaper than, actually running the experiments themselves in a lab, possibly. So.
Absolutely. Like we could even run it, create different kinds that are that optimize for different specific things, and then have a chemist look, tell me what you think is best. It's pretty easy. It's very easy to do and very straightforward to do.
Okay. And then the second thing, and I mean, both of these are, I'm asking about user features at this point. So is it fairly, you talked about the footprint or the fingerprint. Is it fairly easy to take the fingerprint data and load it in if a chemist has, experiments that they've run? So would it be easy to go ahead and get laboratories all across the world to plug data in?
Yeah. So actually, a way to computationally represent molecules is not with the fingerprint. It's called Miles pattern. It's like a string that uniquely represents a molecule, and it's very well known. Those are very well known. There's also kinds of files that are called mole files, molecular files, that people have, and there is ways of transforming those kinds of inputs into fingerprints. That's mainly the reason. That was the focus of my first summer. Okay, I have a common name for a molecule, how do I get from that to that to that to a fingerprint? So I know the pipeline to get from one place to the other. And it's fairly easy. Someone who does work in bioinformatics or knows about this definitely can get those inputs.
Great. And so that would be simple to load in.
Yeah, it would be very simple to load.
Okay.
There are tools that do maybe not this, but you put as input this miles or this mol files and then get output.
Okay.
They already exist. So
it sounds like that's the next step in, getting additional data into the maybe.
Hopefully.
Well, thank you very much.
Thank you.